Hey, welcome guys, and I am here today. An exciting problem today, unlike the other like posts and videos. We will be discussing on a certain problem today. This problem really attracted me. The statement, the real statement of the problem really attracted me. So I thought of discussing it with you. And of course, there will be problem from the food for thoughts that we usually have in our courses. So the idea is simple. The question is very simple. The question asks you that can two or more events be exhaustive or not, exhaustive and independent or not. So events can be exhaustive if the union of them constructs the whole space, and independent if there are certain conditions. Okay, it depends upon how many how many events are there. So I will discussing the simple stuff. So to make it very simple, let's do it for two events. Okay, two events. So if we do for two events, let's do it for two events. So let's define the problem first. So S with a sample space and A, B are strict events. That means A and B cannot be S with probability P and Q. Okay, it's not P plus Q is not equal to 1. Okay, but P and Q I just give it two real numbers, I say. And therefore we have the two conditions are the following, that we have P of A intersection B is equal to P of A into P of B. That is P into Q. This is the independence condition that we all know, and also it can be as P of A given B into is equal to P of A. But here we want in terms of intersection. Okay, you will see where it's used. And for P A of A union B is equal to P of S, it's a entire space is equal to 1. So these are the two conditions, mathematical conditions. Now the question is that can there exist such A and B? If yes, how do they look like? Okay, so you're sort of characterizing the sets, all such sets that is possible. So intuitively I will tell you something. What do you think intuitively? So it's still that A and B are independent, that the probability of one given the another will not be varying, like will not be changing the initial probability of A. uh, so just like this result, that if A intersection B is equal to phi, then A and B are independent, that means A and B can be S with D. Similarly, does it do you what do you think if A union B is equal to S? We know that if there's an element that is not in A, that must be in B, right? There's a if and there is an element in S that is not in A, that must be in B. That's also a lot of information. So can there be independent? Can they be independent? I personally think intuitively it's not. Okay, so you must always think the problem intuitively, otherwise you will get lost sometimes in the mathematical equation, which is not all probabilities about. So let's try to do it from the very scratch ke liye let's do it. So let's define it like this, that if A and B are two events and they have an intersection part, of course. By the end, it is called principle of inclusion and exclusion. So how do you prove it, guys? It's very easy. You just prove it from the diagram. You understand that there is, let's call this part X, let's call this part Y. So X plus A intersection B part is A, the entire A. It's like very crude notation. Okay, it's a union, and Y union A intersection B is equal to B, and the intersection is A union B. So now A plus B, if you do A union B, what you will get, sort of, you will get that it's X union A intersection B plus sort of Y union A of A intersection B minus this A intersection B is counted twice, so we subtract this. So this is A, this is B, so that's why we get this result. This is very crude notation. It's like probability here will be, but I'm just giving you an idea what is happening. There's disjoint events, so probability behaves in that way. The properties of probability, axioms of probability. So we get this result. Okay, we get this result that probability of A union B is equal to probability of A plus probability of B minus this to come like it's counted twice, so we subtract it to like count to the perfect way, in the perfect way. So probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So let's replace that, guys. So you have 1 over here, since A and B are exhaustive, this P is A, this minus this. So if you just if you rearrange it, you will get that 1 minus P minus Q is plus PQ is equal to 0. And I'm sure you must have encountered this sort of idea, this factorization idea in your school. It's actually equal to 1 minus P into 1 minus Q. You can also do it by middle term factorization. Okay, you will get this. So what you get that P is equal to Q1 or Q is equal to 1. you must get this. So what it means? It means that one of them must be S, or rather, if you think in terms of measure, in higher statement, like that's like it should be strict can be possible, but the idea is that for discrete it's not possible. For let's say for in a case of, let's say, real number line, any distribution in real number line, the probability, if you just remove one element, the probability remains the same. So in that case it's not strict in that sense, so it's actually possible. Okay, but for discrete it's not possible. Okay, when each and every element matters. For continuous case it can be possible. So the entire idea is it's only possible when probability of a or any one of the elements is actually equal to 1. Okay, so this is the basic idea. This is the basic idea. Now the natural question is that, it's a very easy proof, very beautiful proof. The natural question is that, what if there are n events? What if there are n events, and can there be n exhaustive and independent events? By the way, till this point of time, if you have not subscribed to our channel, do subscribe if you're liking this content, and spread this to your friends who are really interested. And we are starting a BSTAT honors free 1 month free course from tomorrow actually. Yes, and so we have an exciting 85 people enrollment. So yeah, it's gonna be really exciting. If you have other friends or juniors for first and second year, we're mainly doing this. Do share this with them. You can go on this site. I've given the link of the post here, and you can click over there and get it. Okay, and similarly here, okay, you will get the entire solution here. So similarly, yeah, you can. I hope to see you in the class. Okay, coming back to the problem. What if there are n events? Okay, what if there are n events that you can't do, like want to see, is it possible for the n events to have the same idea? Okay, what is that? The main thing, there's one interesting idea that I have encountered with my students, is that what is the meaning of independence in higher dimensions? Okay, if you go to 3 dimensions, you will see 3 events. You will see probability of A intersection B is equal to probability of A into probability of B, probability of A B intersection C is probability of B C, and there are 4 conditions. Okay, probability of A intersection B intersection C is equal to probability of A B C into probability of B into probability of C. Now, if you go to n events, it will be really complicated. So what is the meaning of independence? The meaning of independence is really simple, that A1, A2 dot an are independent if for any subset AI dash is less subset of this, AI double dash subset of A2 dash subset of A2 and containing any subset. Okay, for any subset, like if you condition on some set of them, the probability of the remaining set will be remaining the same. Okay, so if you take any subset of this and you condition it on another set of disjoint from this, the probability will be remaining same of this. So this is the definition, the generalized definition. Okay, and it's very hard to work with. So it's very hard to work with. I mean, in real life scenario, it's very hard to work with for any independent. But the idea is that for any subset you take, for any collection of subset, another disjoint collection of subset, that is independent. That is the idea. Okay, that is the main idea. That's the main idea. Okay, so keep this in your mind. So if you boil down those, I have explained to my students, if you boil down this 3 events, you will get those 4 conditions only. Those are the minimum conditions you need. Okay, so now for the food for thoughts, one of the most important events, you will see that it's not if and only if, it's a if condition. If they are independent, then this will happen. If any events are independent, then you will see that A1 intersection A2 intersection A3 dot intersection AN will be equal to, we're distributing, okay, probability of A1 into probability of A2 dot probability of AN. So we'll use this condition over. It can only, it will only hold if A and AI is independent. So it's given AI independent, and also its union is 1. Okay. So how will we write this in a very good mathematical way? So we write this in a very succinct way in this: union over 1 to n AI is equal to 1, and probability of intersection of 1 to n is equal to pi. This is the product sign of probability of AI, the product of this. So this is a beautiful way of writing this. And and what we have is that, so let's try to understand, can you sort of change the union to intersection? Yes, we can do that by De Morgan's law. So let's try it out, guys. So get that 1 is equal to probability of this, which is actually equal to 1 minus probability of union n complement, right? And you get that this is 1 minus by De Morgan's law, that it's intersection of 1 to n ai complement. And from here, now ai's are independent, so therefore ai complements are also independent. So if a and b are independent, then g of a and g of h of b are independent. Okay, g and h are functions of a and b. So therefore you get that it's product of probability of ai complement, since they are independent. Ai complements are also independent. So what do you get over here? 1 is equal to this, so you get that probability of, you get product of the probabilities of ai complement is equal to 0. That means what, guys? That means one of them, probability of one of them, ak complement, must be equal to 0. That is, probability of ak must be equal to 1. Similar thing, that we will get one of the one set of them which is just a probability is equal to 1. So this is a very interesting proof of it. Okay, so it's a really beautiful proof and it's a really beautiful understanding. I have told you that there cannot be two disjoint two subsets like this. I have given intuition also, that because if you say that there is one element which is not in one of them, that means it must be in the other one of them. So if there is an element here which is not in A, that means it must be in B, because A union B is exhaustive. So that gives the information about, so given A, that gives the information about B. So in fact, therefore, it's not independent. Okay, it's dependent very highly. That's why it's coming out to be the entire probability is equal to 1. So this is a beautiful idea, guys. I hope you enjoyed the video. And if you have enjoyed the video, do subscribe to our channel and share the beautiful thoughts. If you have some other way of doing it, if you have some other generalization of this problem, do let us know. And I will see you in the next video, guys. Stay tuned and stay blessed. Bye-bye.